Hi everyone, here we go with the week of April 20th, and we're going to work on some equivalent fractions. I know this is different for all of us, so have a little patience with me and as we work through these changes. This slideshow will take us through Monday through Friday, so you'll pause after Monday's work. There will be some work posted for you to do on Seesaw as a way to check in, and then go ahead and go back the next day for Tuesday, and so on. So here we go. We're going to talk a little bit about equivalent fractions for today, Monday, April 20th. A couple things that might be helpful for you to have with you as we go through some of this work is a paper and something to write with on that paper, so you can jot down some notes or record your thinking as we go. Another thing that I thought would be helpful through this week for you to have handy as you do your work is the fraction strips. We colored them in all different colors. I can't find the exact one that we did in class, but I found this example. It might be in your math folder, and I remember we shaded them all in with colored pencils. Each bar was different, but this will help you see some of those equivalent fractions as we work through some of this, and would be a really helpful tool. All right, here's a problem for us to think about. I imagine that we're at the carpet right now as we do this. So this says Mr. Ramos wants to put a wire on the wall. He puts 9 nails equally spaced along the wire. Your job is going to be to draw a number line representing the wire. You'll label it from 0 to 1, and then you're going to mark each fraction where Mr. Ramos puts each nail. It's key to remember that 0 and 1 will also be on there as you put your 9 nails on the number line. Go ahead and jot down on your piece of scratch paper what your number line would look like. And I'm going to try and show you on here while you're working what that might look like. Let's see how this goes. So remember, it's easiest to put your mark for 0, for 1. It's going to be really hard for me to mark on this, it's tiny. And since, and then I'm going to go right in the middle. And I'm going to go in the middle of that, and the middle of that, because I know this is one of my marks. Now I have 2, 3, 4, 5 marks. So if I count the 0 mark, because that's one of the nails, 0, so that's 1, mark 2, 3, 4, 5, 6, 7, 8, 9. And then if you would label all those fractions, that's going to be a little bit hard for me to do on this piece of paper, on that screen. So I'm going to show you what I did on a piece of paper. So hopefully that helps. So your number line might look something like this. And if you start at 0 and count the number marks 0, 1, 2, 3, 4, 5, 6, 7, 8, you'll realize that you're working in 8ths. Can you also build a number bond with 1 in the middle and use unit fractions to show what that whole would be? So think about what was the unit or the unit fractions that we worked with on this number line. I'm going to write 1 in here. It's hard to write on this screen. So how many 8ths would we need if we only can use a unit fraction? There's your key word. We can only use a unit fraction to get up to 1. So we know that our unit fraction, uni, is 1. How many of those would you end up using? Go ahead and take a moment and put that on your paper. Your number bond might be starting to look something like that. Can you see mine? So we're working with the unit fraction 1/8, so you're going to need 8 1/8ths to equal a total of 1 whole. The next part is, what is the fraction that represents 1/2 of the wire? So what is the point? Which nail is on the point that would be 1/2 of the wire? So maybe down in here, I'm going to write know we've spent a lot of time talking about equivalent fractions to a half, and one of the ways that we can see that is that the numerator is 4 parts, the denominator, the types of parts, is 8, and we know that 4 out of 8 would be half of that. So if you had 4 M&Ms and I had 4 M&Ms, we'd share them equally. So our equivalent fraction for half on this number line would be 4. Oops, not going to see that. 8s. Okay, let's go to the next. Think about what you see on this slide. Like, what shapes do you see there? We might have some conversations that they are all 4-sided. You might be seeing a rectangle, which could be true. Some of you are saying that you see a square. All 4 sides are the same. Remember that a square is a special rectangle. Some of you might also be thinking of a quadrilateral or a 4-sided shape. Do those shapes all look like they are the same size or different sizes? As we work on comparing fractions, we have to remember that it's important that the size of the whole is the same. So if I look at these shapes, I feel like I can see that they are all 3 of them are the exact same size shape. And then we can look at these shapes and also see that a fraction of them is shaded, or a part of them is shaded. You name the fraction of each of these shapes, the shaded part. So for this first one here, we have 3 sections, which would be our denominator, and one of those sections is shaded. So below here, I'm going to go ahead and write that I have 1 out of 3 parts shaded. In my next square, we can see that there are 2 parts shaded, and that there are 1, 2, 3, and I can double that and see that there are 6 total parts. So that would be 2/6. In our third shape over here, as you're thinking about this, and I bet you're writing this on your scratch paper, we can see that there are 3 parts shaded. Ooh, that looks horrible. I'm going to try it again. There are 3 parts shaded, and I can see that there are 3 rows of 3, so I can go 3, 6, 9 parts as my denominator. Oops. So we have, in the first square here, we have 1/3. The second square, we have 2/6. And in this third square, we have 3/9. Do you notice that any of them might have something in common? If I rearranged the way some of these shapes are facing or the way that they're shaded, do you think that we could compare these? If I look at this first one for 1/3, and I know that all the other shapes, they're all the same size shape. If I could imagine sliding this shaded part there and this shaded part there, maybe else. Can you see a connection between 3/9 and 1/3? For the middle shape, it might be a little trickier to see. I imagine rotating this square so I can see this part all on the side. And then I can envision those same 3, these lines, but see, they're just going the other direction. And if you imagine removing this line, you might be able to see that 1/3, 2/6 are the same thing. So we can say that 1/3 is equivalent or equal to 2/6, and 1/3 is equivalent to 3/9, which would also tell us that 2/6 and 3/9 are equivalent. Here on this page, we have several different figures. And if we think back to the previous slide, we might think that looking at these, as we look, they are all the same shape and all the same size, yet shaded in differently. I turned my camera off so I can write a little more easily on the screen, I hope. So on this, if you want to go ahead and take some notes about what you would record to identify the shaded part of each figure. I'm going to start up here in this top left corner. So this shape, we can see there are two parts, and one of the two parts is shaded. I'm going to move down my page, this below the 1/2. I see 1, 2, 3, 4. You can even touch and count 2, 3, 4. 4 parts are shaded. Out of 1, 2, 3, I can double that and say that there are 6 parts. Down here, I can see 1, 2, 3 are shaded, and there are 4 parts total. This one looks similar to the one we did on the other page. So I see 3 blue sections, and there are 3, so I'm going 3, 6, 9 sections total. That might make it hard to see. Okay, and let's go back up to the top of this right column. We have 2 parts shaded out of 3. We have 1 part shaded out of 3. Back to that 1/3. Now I'm seeing that there are 1, 2 shaded, and there's 1, 2, 3, 4. Sorry, I had a little technical difficulty. In this shape, we see 1, 2, 3, 4, 5, 6 are shaded. And sometimes I look at what's left after I just counted up those 6, so I can go count on from 6 and go 7, 8. So 6 eighths. Now our job is to see if we can match any of the equivalent fractions on this page. Do you see any that you would match that say they have the same amount of space shaded, even if the name of the fraction is slightly different? Let's start with 1/2. If I look down here at 2/4, it's almost if I can envision this 1/2 being flipped around. And if I can envision also removing this diagonal line, I can see that it would almost look like 1 out of 2 parts. So I can see that 1/2 and 2/4 are the same. When we were looking at 3/9 down here, it does remind me of the previous images we were looking at. And I remember that if we slid these blue shapes over, that I could see that it's that 1 out of 3 of the columns. So that is equivalent to 1/3. 2/3 up here, and I'm looking around, but again, I can envision if I slide over here on 4/6, this blue part right over here, then I can see that that's like the 2 columns of here being shaded in. So those would match and be equivalent. This seems to be the 6/8, it's the most complicated, but the more I look at it, I'm wondering what if I move this section right here and envision it filling this space down here instead? Can you see that that would leave this all white? Remember, if we move this blue section down, that would leave that all white, which is it's exactly the same as 3/4. Okay, on this page, we're going to go ahead and fill in the missing parts of the fractions. You can see that we have pairs of figures that are, again, equivalent to each other. So they are the same size and same shape. Then this first one, we have 1/3 is shaded. So we have in the whole is partitioned into 3 equal parts. The equivalent shape next to it is partitioned into 6 parts, and 2 of those parts are shaded. So we have 2/6. you can see that it's like they took the same 1/3 and partitioned each of those one more time. And my sloppy writing on this screen, I apologize. The next set, we have 2 are shaded, and we can see that there's 2, 4, 6, 8 parts. So 2/8 are shaded, which is the same amount as 1/4. Can you also visualize how that would be like taking the same 1/4 figure and partitioning it once more down the middle? Not very exact, but as good as it's going to get on here. In our final pair of shapes, there are 4/8 shaded in the top, and you can see how they partitioned each section once more, so they're doubling the number of parts. So I know that if I doubled the number of parts shaded, that would be 8 parts shaded, and I would have to double the number of total parts in my whole. So doubling my 8 parts would give me 16 parts. These questions down here, I think, are worded a little bit confusing, but we're going to work through them together. So it says, why does it take 2 copies of 1/8 to show the same amount as 1 copy of 1/4? Explain in words and pictures. So this is something similar to what you're going to do. So I just want you to listen real carefully. So on this, we can look at the diagram above in the middle that shows the 1/8 and how we had to double the number of 8s in order to be the same amount as 1/4. Because we copied again. So I did this on paper because it's a little bit hard for me to write on that screen. Let's see. So 2 of 1/8 to show 1/4. So there are double the equal parts in 8ths than in 4ths. So you need double the copies. So they're using this word copies, which makes it a little bit confusing. But I hope the diagram, I flipped it around a little bit. Instead of partitioning it horizontally through the middle, I did all vertical lines to show the 2/8 is the same as 1/4. This next question says, how many 6 does it take to make the same amount as 1/3? So this is the first set of diagrams here. So we just did that, and it's very similar to what we were just talking about for this. So 2 6 are needed because 6 are twice as many as thirds. So you need twice as many. So it's a very similar idea. Let's see if you can see this. So again, I did the diagram. I made horizontal bars this time, and I showed 2 6 on top shaded in with 1/3 in the second bar shaded in, and that's the same amount. You can kind of see that it takes 2 6 to make each one of those thirds. This final one is kind of an extension. It says, why does it take 10 copies of 1/6 to make the same amount as 5 copies of 1/3? So if you think back to the previous question, we were doubling the number of parts. So you might even think of 10 and 5, their connection to each other. So if you double 5, that's how you get 10. So we're going to have to double the amount. So again, 6 have twice as many units as thirds. So you're going to need twice as many parts. Not 5 parts, but you'll need 10 parts because when you double 5, you get 10. So this is more than a whole. So we have less than 2 wholes, but more than a whole. Do you miss my little thinking bubbles? Let's see. I can't get that on the screen. So if we have 6 6, that is 1 whole, plus 4 more 6, that gets us to 10 6 total. So we're not quite at 2 wholes, but we are definitely beyond 1, close to another second whole. With our 5/3, which is the same as 10 6, so 10, so our 5/3, 5 had to get doubled to make 10 because 6 are double of the thirds. So here we have 3/3, that is 1, and 2/3, which is the same as this 4 6. And of course, you know 3/3 and 6 6 are the same. So 3/3 plus 2/3 is 5/3. Okay, this will be the practice that you'll do independently. We'll review some of the things that we talked about on the slideshows so far. These 3 pages will be posted on Seesaw, so make sure you put an effort into all 3 of the pages, and when you're done with all 3, submit them, and I will be able to check them over and see what your thinking was. Go ahead and write and draw right on there. If that is not helpful, go ahead and draw it on a piece of paper and take a picture of that and send that over to me also. I can't wait to see what your thinking is about these things. Do your best and have fun. Also, remember to keep working on your multiplication facts. I'm sure you're doing that. I put that in some notes that your parents will see also. And you can pause this video now and come back to this point tomorrow for Tuesday. All right, good job. Okay, you're back for more. It's Tuesday. This will be shorter. I'm mostly just going to post some things for you to do on Seesaw and remind you of some things you can practice at home. Keep up the great work. I know you all are working really hard and doing a great job in this different remote learning time. All right, I just want to talk through a little bit about what Tuesday's work will be. Tuesday, I would love for you to work in your Math and Focus Workbook B. That's the workbook that you picked up at school like a couple weeks ago. On that Friday, Miss Lee and I were waiting for your families to come by and pick up things. So when I put MIF, it just stands for Math and Focus. Please work on pages 91, 92, and 93. I don't necessarily expect somebody to correct that with you at home. If that's something that can happen, that's totally fine. It's up to you. One thought or idea could be that you would circle one or two of the problems that were interesting or maybe challenging for you, and you want to have a conversation with somebody at home about those problems to make sure that you have a chance to practice talking about what you did and also to share with somebody at home some of the thinking and work that you're doing. On Seesaw, I'm going to post an exit ticket. So just like in class, you can go ahead and code it with the green, yellow, and red mark to let me know how you're feeling about answering the question on that exit ticket. It will have some number lines on it. When you're ready to submit your work, go ahead and submit your work and I'll check it from there. Some of you are very excited for more math tiles. So I'm going to post 3 new pages of math tiles up to Seesaw. You can find your math tiles, the individual tiles that have 0 through 9, the digits, all the digits on them, so that you can work that way. If you can't find them in your math folder, maybe you can go ahead and be creative and make a new set of tiles. When you finish the 3 pages of math tiles, you can submit them and I'll go ahead and check them over there. I can't wait to see your work and thinking on that. So that's all for Tuesday. And you can pause here, go ahead and do some of that practice work and come back for Wednesday. Okay, we're moving on to Wednesday, April 22nd. I don't know about you, but I'm having a hard time keeping track of the days not being at school. So hopefully you're picking back up after you did our work together Monday and Tuesday. A reminder of some materials that would be helpful. So the fraction bars are helpful because you can have a visual in front of you of how some of these fractions are equivalent to one another and some are not. A paper or pencil, something to write with to help you take some notes or jot down some thoughts as we go through this. All right, so we're going to count together using these number lines to help us see what we're going to count. If you look with me on this top number line, I can see that there's a 0, a 1, a 2, and it goes beyond 2. You can also see that the line has been partitioned into equal parts between 0 and 1, and the same type of partitions from 1 to 2. Looking at the second number line, I see that we also have a 0, a 1, and not a 2, but I would assume that here would be a 2 because the 1 was at the same spot as was the 0. So it seems to me we maybe could guess and decide that there's going to be a 2 there. I want to write it in. Let's see if we're correct. All right, before we get going though, we have to figure out how many parts we have or how many little mini parts or jumps it would take us to get to the one whole. So on this number line, maybe I'll see if it'll let me draw. I'd have 1, 2, 3, 4, 5, 6. All right, so I know that the unit fraction that we're going to work with on this top number line is 1/6. So we're going to be counting by 1/6 parts. On the bottom number line, let's do the same thing. So if we start at 0 and we figure out how many jumps it's going to take us to get to one whole. Oh, technical difficulty again. 1, 2, whoa. Okay, 1, 2, I'm going to do it differently. 1, 2, 3. So we have 3 parts to get to 1. 3 mini jumps to get to the 1 whole jump. So we know that our unit fraction that we're working in with this is 1/3. So if you go ahead and count with me, don't make me do this by myself, please. So if we have 0 or 0/6, we can even say here, maybe I'll change colors. Give me a second. All right, so we're at 0, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. And that should make sense to us that we're at 6, 6 at 1, because if you have 6 parts out of all 6 parts that made the whole, then we would have 1 whole thing. So think to yourself, what would happen if you were just counting up? What's after 6? 7. So we know we're going to have 7, 6 as we move beyond 6, 6, or 1 whole. 7, 6, 8, 6, 9, 6, 10, 6, 11, 6, 12, 6. I'm laughing at my marks on the screen. Those are horrible. So 12, 6 at 2. I'm going to write that over here so I can see it. What do you notice about 12, 6? How many 6 are in 2? Wouldn't there be 2 groups of 6 would make 12? So if we have 6, 6 to make 1, and another 6, 6 to make 2, we have 12, 6 altogether. This number line keeps going on, so we're going to go ahead and keep counting. So we have, after 12, 6, we're going to go from 12, 6 to 13, 6, 14, 6, and 15, 6. So our ending spot was 15, 6. All right, do you remember below we were counting by thirds? Ahead of time, do you have an estimate of how many thirds will we get when we're at 1? You might be thinking, we need 3 thirds to be at 1. Anybody have an idea of how many thirds we might need at 2? You might look at this. Might help you see the number of thirds. Let's go ahead and count. So we're at 0 or 0 thirds. 1/3, 2 thirds, 3 thirds. We were right. If we go beyond 3 thirds or beyond 1 whole, I have 4 thirds. Sometimes we talk about that looking interesting when you have 4 parts out of 3 parts possible. You know you've gone beyond the 1 whole because you have more parts that you've used. 5 thirds, 6 thirds. Did you make a correct guess? I bet you did. So 6 thirds is equal to 2. How many 3s are in 6? 2. Makes sense, doesn't it? And this number line is ending at 7 thirds. I'm embarrassed for myself. This whiteboard would look horrible. Let's look at one more thing comparing 6 and thirds together. Okay, I made some diagrams so that we could compare what we did on the number line to a bar. So remember, you can envision having a number line right below your bar. So this would be where 0 would be on a number line. Let's see, maybe I should write that on there for you. You can think about this spot being 0, and this is our 1 whole. And we actually have 2. So if I shaded in all of these bars, at the end of this bar would be 2 wholes. That looks like 12. Same with on this bottom bar, we have 1 whole bar and a second whole bar. So we have 0 when we're here. We'd have 1 when we get over here. And by the time we went through this entire other bar, if we did get to go through all of that, we would have 2 whole bars. So on the previous page, we had been counting by 6. So can you see that if, maybe I'll use another tool that I can see on here. If I shade this section of this bar in, ooh, that's not a good color. These are not going to work out well. Let me erase that for a second. Sorry about that. Let's see. All right, back to the pen. So if I shade one part, whoa, sorry about that. I'm doing my best. Remember that part where I said have a little patience with me? All right, we have 1/6 shaded in. If I continued shading in, I'm going to just do this. You're going to consider that shaded in. Now I have 2/6. As we keep going across the bar, and I try and improve my shading abilities. Oh my gosh, that's horrible. Now we have 4/6. I hope you're laughing at me, with me. That doesn't, can't do that. Let's see if I'm gonna try this little pen thing I have. Nope. Now I have 5/6, and then I have 6/6, which remember, that is equal to 1. What would be the equivalent amount if I was going to shade in thirds? What is the fraction that is equivalent to 1? How many thirds would we need? Third is my number of parts, type of parts. How many parts would be shaded? You're right, we'd need all 3. So I'm going to use a different, oh, that didn't come out. There we go. So let's see if I can shade a little better. Oh my goodness. Not great, but there's 3/3 shaded. But we can see if we go beyond 3/3, let's say that I have 5/3. So that would be this 4th third, and now I have 5/3. So I have one whole bar that's shaded and a second bar partially shaded, but not all of it. We still have 1/3 not shaded. Can you see what that would be equivalent in 6? So right now we have down here 5/3 shaded. How many 6ths would I need up here to be equivalent? It's back to the work that we were talking about on Monday with if we double, we need double the number of 6. So if we look at our denominator, thirds, our 6th is double. Because remember, it's like partitioning it again. So that would mean I'm going to need double the number of parts shaded because they're smaller. So let's see if that's going to be right. Can you see if I draw a line from the end of the 5/6 all the way up here where that might be where it ends up? So we know so far we have 6/6 shaded in, and that I'm trying to figure out how many more. I'm going to go to 5, oops, 7, 6, 8, 6, 9, 6, 10, 6. Is that what you thought it was going to be? So we doubled the number of parts by making them smaller. So we had 6 parts for each hole. And that would mean we'd need to double the number of parts shaded. So we have 10, 6. All right. Wednesday's practice that will be up for you on Seesaw. I hope you're getting used to that platform. I'm enjoying seeing all your work. It's really fun to be able to see how you're finding ways to show your thinking. So on this page, you're going to go ahead and go through, read all the directions really carefully, talk it over with somebody at home if you feel like you want to talk out your ideas. Sometimes it just helps to think and talk out loud before you write down or commit to what you were thinking. So there's 2 pages. When you finish both of them, go ahead and submit it so that I can look for it there. And if it's easy to write and draw right on these templates, go for it. If not, and you want to write on paper and take a picture of that and post it up there, I'm totally fine with that too. All right, have fun. Come back for Thursday. Hi everybody, here's what you're going to work on for Thursday. We're going to go back to Math in Focus Workbook B. Again, it's the one that you picked up at McGilvra. Miss Lee and I gave each student a math workbook, some pages, and some, I think it was a grammar workbook. For today's work, if you would go ahead and work on pages 94, 95, and 96. Again, you can circle 1 or 2 problems that were interesting or challenging and have a conversation with someone at home about those problems. There's a couple other task pages similar to yesterday's work that I'm going to post on Thursday for you to work on there. Math tiles. Remember, those math tiles that I had put up earlier in the week, those were not meant for you to do all at once by any means. So just continue working on those at your own pace. And when you're done with all 3 pages, go ahead and submit them on Seesaw so I can see your work. I'll put more math tiles up next week. So if you're done working on those, I get it. Don't forget, keep working on your multiplication facts too. Hi again. Okay, it's Friday. We made it to the end of this week. We're going to continue our work on equivalent fractions, and we're going to think about different ways that we can continue using number lines and pictures, diagrams, but also finding some ways that we can use some mathematical operations to also find equivalent fractions. A reminder that these are some materials that would be helpful for you to use and have handy as we work. All right, we're going to look at an image of some avocados. I bet some of you are huge fans of avocados, maybe even guacamole, and maybe some of you are not, and that's okay too. I'm a huge fan. Sophia's only starting to like guacamole, but will not just eat an avocado. I'm working on it. All right, so what do you see besides avocados? What are some things that you notice? How many avocados would you say that you see there? Are you finding groups that you can count them by? Is each one of those a whole avocado or a part of an avocado? Some of you might be noticing, gosh, if I put this avocado, this part of the avocado with this part of the avocado, they look like they would go together to make a whole avocado. Does that change your thinking? Maybe you want to count these up. Because if you look at them now, you might be saying, oh, actually, those are half avocados. So how many half avocados do we have? We could say we have 1, 2, 3, and I know there's 3 in the next column also. So 3, 6, 9, 12, plus 3 more is 15, plus this one down here, don't forget that. So we would say that we have 16 halves. How many whole avocados would that be? If you put them all back together. Do you remember that this is also a division equation? 16 shared by 2. Yep, 8. So we have 8 whole avocados. Could we also say how many fourth avocados do we have? Can you see a way that you could do that? If this avocado part is half, what would we need to do in order to see that as a fourth? Can you see that you would partition it one more time? So we have to double the count that we're going to get. So if I had 16 halves, and each time I see a half, that's actually, I'm going to count it twice. That means I'm going to double this. So that means we're going to have 32, not 32 avocados. 32 what? "32 fourths." Oops. 32 fourths. Do you see any connection between the 8 whole avocados? We could also say that is the same as 8 over 1, or 8 wholes, 16 halves, and 32 fourths. Did the amount of avocados that you see in this picture ever change? There was no magic, right? Same number of avocados the whole time. We still have 8 whole avocados. We can look at 8 whole avocados as being 16 halves. But we could also look at it differently and say, oh, 8 whole avocados is also 32 fourths. How do we go from 8 whole avocados to 16 halves to 32 fourths? Let's see what we can find out. All right, I turned my camera off so I can work this out a little differently on this tablet. So remember from the previous page, we said that we had 8 whole avocados. And in a fraction form, 8 over 1 is the same thing as 8. We looked at how many half avocados there were, and we found that there were actually 16 halves. And we know that the amount of avocados never changed, so that 8 whole avocados is the same as if you had 16 halves of an avocado. We looked at that again and said, oh, but we could count it differently. We could count it by fourths. So then we had 30. Let me get rid of that. 32 fourths. When you look at the numbers, do you see any patterns or things happening with our numbers? What if we just looked at from 8 to 16, and then from 16 to 32? So from 8 to 16, what happens? From 16 to 32, what happens? Some of you might be thinking it's doubling. And finding patterns, we keep looking. If we look at our denominator, what is happening with our denominator? From 1 to 2, from 2 to 4. Both our numerators and our denominators are doubling. The amount of our avocado never changed. We just called it a different name. Would you agree when we talk about doubling, we talk about groups of 2? Because if we do 2 groups of 8, we get 16. And 2 groups of 16 gets us 32. 2 groups of 1 gets us 2. 2 groups of 2 gets us 4. So it sounds like we're doing 2 groups of. But we did it to both the numerator and the denominator. So let's remind ourselves, what is the same as 2 over 2? What does that equal to? I'm going to put a little thought bubble over here. You know how I like to do those. I'm going to think and remind myself that when I have the same number in the numerator and the denominator, that's always equal to 1. And anytime I'm multiplying anything, we're going to go back to algebra, we're going to use a letter to represent any number. Any number multiplied by 1 will always get me what that other number is. So if I multiply a fraction by 2 over 2, I'm actually multiplying it by 1. So I haven't changed it. It's like we didn't change the number of avocados. We still have 8 whole avocados. We just made it different. Let's try this with our fractions. So if I have 8 whole avocados and I want to find something that's equivalent to it, I can, I'm going to shift colors here, multiply that 8 by 2. But I have to do the same exact thing to the denominator because I know that 2 over 2 is the same as 1. So I'm not changing it, the value of it. I'm just changing the name of it. So 8 groups of 2, you know, is 16. 1 group of 2 is 2, 16 halves. Do you see how we got that? So up here, it would be saying 16 groups of 2 gives you 32. Same thing to the denominator. 2 groups of 2 gives you 4. This is a mathematical way that we can find equivalent fractions. So let's remember something. The picture never changed. We always had the same exact number of avocados. We always had 8 whole avocados. So we are showing how we can show that in a more mathematical way. So we reviewed that the identity property, you guys remember that from way earlier in the year when we talked about anything that you multiply by 1 will always be what that other number is. So if I have 3 million groups of 1, I'm going to have 3 million. Or if I have one group of 3,902, I'm going to have 3,902. We like coming up with those, but it's that identity property. It keeps the same identity. And any fraction that is, you guys could even do it. If you know, if you have 100 over 100, it's the same as having 1. Doesn't matter. As long as the numerator and denominator are the same, it means you have the whole thing. So when we turned 16 halves into 32 fourths, we multiplied that by 2 over 2, or 2 halves, which is the same as, so if we have 2 halves, it's the same thing as 1. So that's how we can use this identity property. Do you think that we can go in the reverse? Because we know that multiplication and division are the inverse or the opposites of each other. So if I have 32 fourths, could I use that same idea that any numerator and denominator that are the same will be equal to 1 to go from 32 fourths to 16 halves? Let's look at this. So if I have 32 fourths and if I divide by 2, let's see over here, if I divide 32 by 2, that gives me 16. And if I divide the denominator 4 by 2, that gives me 2. Do you see how we went? We use the inverse, so we can multiply or we can divide. I wonder, can we take 16 halves and get down to the 8? 16 halves. If I divide by 2, divide by 2, it will be 16 shared 2 ways gives me 8. 2 shared 2 ways gives us 1. Now we're back to the 8 whole avocados. But remember, the number of avocados never changed. Let's look at this one more time because I think this is a little bit confusing, but you'll have a chance to practice and see how it goes. If I have 2/3 and I multiply that by 3/3, that equals 6/9. Can you see that 2 groups of 3 is 6? 3 groups of 3 is 9, excuse me. Remember, 3 over 3 is the same thing as 1, so we're using the identity property to help us find these equivalent fractions. This shows that 2/3 groups of 1, or 1 group of 2/3, is equal to 6/9. If we look at this in picture form, here's the 2/3 shaded in the blue. 1, 2 out of 3 are shaded, or 2/3. What we did is we said, oh, I want to make 3. I want to do the same amount, but I need 3 times as many sections. So instead of 1 section here, I'm going to have 3 sections. You see how this lines up right here. So I have 1, 2, 3 sections to where there was 1. So it's 3 times as many parts or partitions to represent that equivalent fraction. But the amount never changed. Let's look at a couple of problems together. What are the missing numerators and denominators? I just took this from a workbook page, so I think I'm going to go ahead and just do this real quickly. Do you see that all the shapes in part A are the same size and same shape? Yes. So they're fair to compare this. That's why we can have these equals here. So this is going to be equal to 2 halves. This is 3/3. And now we have, let's see, 1, 2, 3, 4, and that's doubled. So it's 8, whoa, 8s. And all of those are equal to 1. So that would help us remember that we can use that as the identity property. Here, if you go through here, you're going to see that you have some equivalent fractions. You're going to have a chance to practice this in the math workbook, so I'm not going to go through this too quickly. And then if you see that if I multiply to find this equivalent fraction, 1/3 is equivalent to 2/6. What did 1/3 get multiplied by? Can you see that it was multiplied by 2 halves? So look, 1 group of 2 is 2, 3 groups of 2 is 6. Now we have that is equal to 3 somethings, but we can't multiply 2 by something to get 3. So they went back to this and said, oh, how do you go from 1 in the numerator to get 3 in the numerator? You guys know. It's going to be 3 thirds. So 3 groups of 1 is 3. 3 groups of 3 is 9. Whoa. So you can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's a little bit more practice here. So if we can see that if I have, I'm down here, if I have 1/4, what did 1, I'm going to write it bigger over here, 1/4, I'm trying to find an equivalent fraction where I have 12 parts. You could draw this out, or you can actually go back to that fraction strip sheet too to help you. But my thought bubble is, if I have 4, how many groups of 4 do I need to make 12? What are your thoughts? 4 groups of 3 make 12. That means I'm going to need to multiply 1/4 by 3 thirds, because 3 groups of 4 is 12. 3 groups of 1 is 3. So the equivalent fraction is 3/12. I'm going to erase that and leave that some workspace, and we'll work on 1 or 2 more. Come back and re-watch this if it feels confusing. Let's see. Let's do 3/4. This one right here. Oops. So they're asking us to find the equivalent fraction to 3/4. This is so tricky to write on here. Where did it go? 3, oh my gosh. 4ths. There we go. They're already telling us from this work that they want us to have 6 parts shaded. What we're looking for is this missing denominator. So remember, your thought bubble is 3 groups of something gets us to 6. I bet you see it already. So you know that going from here to here, I need to do groups of 2. And remember, whatever you do on top, you have to do to the bottom because of the identity property. So 3 groups of 2 is 6, which we already had the numerator because that helped us know what to do to the denominator. 4 groups of 2 is 8. So we can see that 3/4 is equivalent to 6/8. They have some examples here that I would have you pay close attention to. Let's look at one other page. So here's some more practice with that idea of finding the missing numerators and denominators. They have some pictures up here for you to work with. And down here, they're showing how we can go in the reverse direction. So using the inverse of multiplication, which is division. So let's try this. So we're going to look at 6/9 is equal to 2 what? So 6/9, and they want us to have 2 parts, or 2 in the numerator. And we're looking for what goes down here. Remember, your thought bubble is, how do I go from 6 to 2? And you can think, well, if I do 6 groups of something, there's no way with a whole number that I'm going to get 2. So that's not going to work. So we know we're going to share. So if we have 6 shared, by how many groups will get me to 2? You got it, 3. So I'm going to do 6 shared by 3 is 2. 9 shared by 3 will get you 3. So that's 2/3. So that's how this can work with the inverse operation using division. A lot of times you'll see these are called this when you use division to find the smallest way you can possibly numbers or smallest number of parts you can use. They call it the simplest form or simplest equation. We'll talk more about that next week. So a couple keys. is that you can use both multiplication and division to find equivalent fractions. But please, please, please remember that you can go back to your number lines, you can go back to your fraction strips, you can go back to making diagrams. All of that is important so that you understand what you're doing. Remember that anytime you have a y over a y, remember that's an algebraic way of talking about this. That means if you have 5 over 5, or if you have 8 over 8, all of those are equal to 1. So it doesn't matter. As long as the numerator and the denominator are the same number, you know that is equal to 1 whole. So that identity property of multiplication helps you to see you're not changing the value or how much you have, you're just changing the name of it. All right, Friday's work. In the workbook, yes, workbook B, so it says 3B on the cover. Please work on pages 97 and 98, just those 2 pages. Again, circle 1 or 2 problems that you can talk about with somebody at home. There will also be an exit ticket on Seesaw for you to work with. Remember, you can use the green, yellow, red check-in system, so you I know how you're feeling about answering that problem, and I'll check your work there after you submit it. And again, you can continue working on those math tiles. Submit the 3 pages when all 3 are done. All right, have a great weekend. You did great. I hope this went okay for you. I will make it better for next week, and I look forward to seeing you there. All right, bye.